Today, what I want to do is actually take a minute and explain to you guys a little more deeply what net force is. You use the net force simulation and you get it pretty well. Let me return to that topic and re-emphasize some things that we've already gone over, but really help it make more sense in your head, hopefully. So let's take a look at the net force simulation. We've all messed with this a little bit by now. Y'all turn to your worksheet in. What happens if I put one blue figure on the line? If I click go, which way is the cart going to move? Left. Everybody says to the left. How do you know that? Can you explain that to me mathematically? All right, it says left force. All right, sum of forces says the force is to the left. There's more force going to the left. There's more force to the left than the right. Okay, good. That's all correct. So let's take a look at it before we do anything else. The sum of forces is 50 newtons to the left. Okay, let's click go. 1, 2, 3, 4, 5, 6, 7, 8. All right, it took about 8 seconds for that figure to get off the screen, okay, to get to the first knot in the rope. Let's reset it. Let's reset it and let's add all of the blue figures. So there's 350 newtons pulling to the left now. And let's put these 3 red figures as 300 newtons pulling to the right. Which way is the cart going to move when I click go? Everybody says it's going to go to the left. Explain that to me mathematically. Why is it going to move to the left? Okay, 350 newtons is greater than 300 newtons. That's true. It's still 50 greater, the left force is 50 greater than the right force. Good. Good. There's more force to the left. Good. That's all mathematical and it's all true. Let me ask you this. At what rate is it going to pick up speed? Is it going to move faster, more slowly, or the same as what we just saw? You think it's going to move faster? Some say the same, some say more slowly. Why? Can you explain that mathematically? Why do you think it's going to be the same? Why do you think it's going to be slower? Why do you think it's going to be faster? Addison says the same because there's the same amount of net force. Okay, some of us say more quickly because there's a bigger force on the left. Some of us say more slowly because there's a bigger opposing force on the right. Some of you say all that matters is this sum of forces, which is another way of saying the net force. The net force is the same. It's 50 newtons to the left. Let's click go. 1, 2, 3, 4, 5, 6, 7, 8. It's the same. So what that tells me is it actually doesn't matter adding up all the numbers. What matters is adding up this sum of forces, this net force. There's 350 going to the left, 350 newtons to the left, but 300 newtons to the right cancels out 300 of this. So yeah, there's more tension on the rope, but the overall force is still 50 to the left. So this setup is exactly the same as what we saw with one little blue figure. And that's what net force means. Exactly. The net force, I'll type this in the chat. The net force is the sum of all forces acting on an object. So those of you that already put that in the chat or put that in your worksheet on Monday, great job. That's what we're looking at. Net force is a sum of all forces acting on an object. And we do need to worry about the direction. It doesn't mean that we add up 350 and 300 and get 650 newtons. That's not our net force. We have to worry about the direction. So I think I can explain this to you visually in a way that'll help it make sense. So I'm going to do something we haven't done in this class before. I've only done it in math tutoring. This year, we're going to use the doc cam live on Zoom. So cross your fingers that it works. Share screen with the doc cam. Let's draw a box in the middle of the page, floating freely in space. Okay, it's not a perfect box. This is just a box floating freely in space. Let's draw the forces that are affecting it. I'm going to make up some values. I'm going to draw arrows to represent those forces coming out from the middle of the box. So let's go out to the right, and I'm going to make each one of these boxes worth the same amount of force. So I'm going to make each box worth 10 newtons of force. So this would be 10, 20, 30, 40, 50, 60, 70 newtons of force going to the right. And let's go out to the left. 10, 20, 30, 40, 50, 60. 60 newtons of force to the left. Now, I know you guys are working on graphing right now in math, and that's perfect. That goes right along with what we're doing. Let's think of this like a graph, and this is our x direction. On the x-axis on your graph, and you move to the right, when you move to the right, is that positive or negative? Very good. Moving to the right is positive. Now, on the x-axis, if we start at the origin and move to the left, is that positive or negative? It's negative, exactly. So knowing that, we can actually set this up as a math problem, so it'll give us the direction that this thing's going to travel. We'll do that by saying the net force equals, and I'm going to write some notation that we use for net force. F with an arrow over it, and in subscript, the word net. Subscript is where you write little tiny letters down on the line. So F net, that's our net force. What can we set our net force equal to? How can we work this out as a math problem? Sydney, I like the way you set it up. Let's just go left to right and add everything up. 60 newtons, but it's going to the left. So is that the positive or negative direction? Negative, good. So somebody got it. Let's start with negative 60, and remember your units, negative 60 newtons. Remembering your units becomes really important when you start doing more complex problems, especially in physics, because you work with all kinds of different units and it's easy to get mixed up. All right, so negative 60 newtons, we got that. And then 70 newtons, is that positive or negative? Very good, plus 70 newtons. Negative 60 plus 70. And so what's our answer? 10 newtons, positive 10 newtons. So because it's positive, is that net force going to be to the right or the left? To the right, exactly. To the right. So we know our net force is going to be 10 newtons of force to the right. Very good. So we are dealing with something here, guys, called a vector quantity. And normally people don't learn about this until physics class in high school or college. Let me teach you about what this is. When we're calculating stuff in physics, there are two types of quantities we can look at. One is called a scalar quantity. Think of a scale. When you step on the scale, what does it give you? Just a number. A scalar quantity has size or magnitude only. That means just a number, like 50 newtons. This has units because we always need units. A vector quantity, a vector has size / magnitude, meaning the number, and direction. It has to have a direction. It tells us which way it's pushing, pulling, acting, whatever. So for example, an IE means for example. I know it doesn't seem like an abbreviation, but it comes from the Latin. For example, 50 newtons to the left would be a vector quantity. The way we write our notation for vectors in physics is to put an arrow above our variable. And you'll also see it in bold typeface if you see it in a textbook somewhere, okay? So if you see me write F with an arrow above it, that means we're looking for a magnitude, meaning the number, and the direction. How big is it, and which way does it go? How much, how many newtons, and in which direction? So let's see if we can do this with a slightly more complicated problem. Oh, but before I do that, this diagram I just drew for you, it has a special name. And this is what we're going to be doing next week. We're going to be working with something called free body diagrams. A free body diagram doesn't mean we're giving stuff away for free. It means body refers to the object, and free means that it's just floating in space, not really attached to anything, not touching anything, only things that are exerting a force on it. So we're just drawing an object floating in space and then notating with our arrows all the forces acting on the object. And this is how we do complex problems where we figure out, like, well, what if I let go of this box? What direction is it going to go? And what if there were 3 or 4 or 5 different forces acting on it? How do we figure all that out? Let's do a slightly more complex problem, and then we'll be done for the day. Another free body diagram. Box floating in space. We'll draw our arrows coming out from the center of the box so we can look at their magnitude. I'm going to draw them and then I'll measure them. All right, so this is 40 newtons to the right, and 1, 2, 3, 4, 5, 60 newtons to the left, and 1, 2, 3, 4, 5, so 50 newtons down, which would be the negative direction on a graph, and 10, 20, 30, 40, 50, 60, 70 newtons in the positive y direction, or up the y-axis. Now here we're dealing with x and y, so we can actually split the net force apart into its x components and y components to set it up. And the way we write that, F net x and F net y, okay? So now let's deal with just the x, and let's color code it to make it simple. Let's look at all of our x, so our rights and our lefts, that's gonna be our x direction. And then let's look at our ups and downs, our y direction. All right, somebody tell me, how am I gonna set up our net force to the left or right? How am I gonna figure that out? Good, let's just go from left to right and add it up. So 60 to the left is the same as saying negative 60 newtons. And then 40 to the right is like saying plus 40 newtons. And so we add that all up together and we get equals negative 20 newtons. So the negative x direction. It tells us the direction in our answer. Negative means to the left. Perfect. All right, what about the y? Let's set up the y. Okay, We can go bottom to top, top to bottom, either way. So good, see, you guys already know it's gonna go up. You can tell what the net force is gonna be. So F net of y is gonna be negative 50 newtons plus 70 newtons equals 20 newtons, positive 20 newtons, which means up, Good, we have one more minute in class. So we know what our net force is gonna be. Let's draw it. Let's draw just the net force. So imagine that you could actually see the net force as an arrow. What's it gonna look like? Well, it's gonna look like 20 newtons up, and it's gonna look like 20 newtons to the left. Sorry if my handwriting's a little scribbly. So this is our net force, or our F with an arrow, net. So if I let go of this box, which way is it actually gonna go? There's these forces acting on it in space. You think it's gonna stay? Or somebody thinks it's gonna go diagonal. Well, what we actually do is we use a little bit of trigonometry and figure out which way this thing's gonna go. And we find out that actually, if we treat this just like a slope, just like a slope in graphing, if we go to the left 20 and up 20, figure out that that's actually the way it's gonna move. And if we measured this, we could figure out how much force, because it's a little bit more than 20, our net force. We can also use the Pythagorean theorem that some of you have heard of to calculate what that's gonna be. So we know that our net force is actually this right here. Oops, I barely read F net now. Thanks, highlighter. So that's our net force. It means when we add up all the forces, which way is it gonna go? Well, look, we have all these big forces in different directions, but when we let go, what's gonna happen? We're gonna be left with boop, 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 boop. That, the dotted line, our net force. It's gonna move up and to the left diagonally with a small force. Okay, so we covered net force. We covered subscript notation, we covered free body diagrams, and we tried to tie it in to graphing skills that you guys are gonna use in math. What I just showed you, that's like a problem I had in my college level physics class. So if it's making a little bit of sense to you, great, feel awesome, feel amazing. If it's a little bit confusing, that's okay, you're in 8th grade and you're doing awesome. We're gonna keep working on it together, and eventually I'll give you guys some problems to work out to calculate net force, and we'll use it in applications here in the classroom. So great job, guys. Class is over. Go have a fun afternoon. I will, oh, and do your homework. Okay, bye.